Today's date is the 20th of May 2026. The time now is 6:39 p.m. Yes, so today I'll be having the OBI, uh, OBI executive summary, ontological Bayesian intelligence, authority system, the ontological summary. I've got the book here by Timo Kowski, and John M. Noble on Bayesian networks, an introduction. And this is the book I'm studying to build the AI systems and robotic interfaces. Well, this is theory for the theoretical aspect of the paper written. I'm gonna be showing you a lot of things here, but this is basically an extension because the first one wasn't very formal. This is a formal summary of the ontological Bayesian intelligence or OBI system, the heart AI system, the heart AI specification. Ontologies refer to system state uh, and its knowledge of those states. Naturally, by definition, ontologies refers to system states and knowledge of those states. Internal knowledge K, such that D, data, implies state. External knowledge K, such as S, state, external state, implies D, data. Where K is knowledge, D is data, and S is state. Um, but this is basically a system that knows itself. It knows itself before it can act. It has a reference to itself, so it knows what it's acting upon. You know, uh, Bayesian. The thing I want to express is it's basically a Bayesian theorem, Bayes theorem proof. This book, Bayesian Networks, an instruction, is by Tim Koski, and John M. Nabel. Basically, in this book, they explore how to formalize things, formalize graphs, knowledge graphs, probability graphs, such as I haven't really read it, but it's used in classrooms, in lectures so you can perform case studies. And OBI is a case study or the OBI kit on github.com /OBI MK2 OBI is a case study. Is a case study kit. It's like, does my system know itself or not? Does to act to make certain decisions. Know yourself is it's like a system knows itself. It knows what it's doing. It knows how to act on external external systems that are in this frame of reference. The Bayesian network book is literally the thing I'm studying, but kind of informally. But I haven't got into the proof here. So I've gone to the proof here. I've got the proof down, but this book is a fundamental piece of my work. It goes through the Bayesian rules and evidence of case studies to explore certain relationships of functions um, um, or via differential and integral calculus and standard functions like independent variables, dependent relationship between functions, confederation, priors to like confounders. Like the example I gave last time was support structure in Nigeria and the UK. We have a very bad support structure in the UK from the government, but we have localized support structure in the UK. So neurodivergent people are not disabled as UK neurodivergent people, or if not, not at all. Because the confounders are a relationship that is like a gray area that. The confounders that give a sense of uncertainty that provides sort of uncertainty, because it makes it hard to take political risks. It brings noise, because you may be there, but you're not measuring it. You're not measuring for the right thing. Because your test is it's hard to pick out what to measure from that unless you have clearly identified the problem. Follow along. You get things like dependent variables, independent variables. All of this can be modeled by probability graphs, which are Bayesian semantic graphs with probability between 0 and 1. So let me get into some of my work now, and I'll show you why this matters to me. To me, so we have my overleaf work, and I can see it's quite a lot here on Muko ontological Bayesian intelligence. This is all my work on the projects of the Muko ontological framework. Some of them are named badly, almost typecut, but they are real systems that can be put into real world models to ensure that they work as intended. They are real frameworks. So I'm gonna be reading some of them. So we're gonna start with unbiased AI. These are the principles of the system here. We have hypothesis 1.1, confounders to Bayesian networks and bias parameters. Uh, uh, a bias parameter. It's a I can't remember what this was. Uh, yeah, how do I define a bias parameter here? So you got the input data feed into the Bayesian network, and the Bayesian network has a device apple uh, based on the bias parameter. Because there's some independent, my understanding of this in this framework is they are given a case study, they are dependent and independent variables that the bias framework can tweak or enhance to ensure the bias output. And the bias output is 100%, cannot be 100%, or can be 100% if there's a bias parameter involved. That's what I'm trying to claim here. Because traditional AI has a black box. And because it's a black box, you have a bias output. But those have some hidden bias in the data based on how you collect the data. So think of the bias parameter as independent and dependent variable tweak, dependent independent variable tweaking, where the independent variable, based on how you carry out the case study, to or settings of a vector. If it's in a vector database, like a traditional AI vector database, you can tweak out based on or tweak in a relationship, or tweak out or tweak in something that controlling the probability state of the system. Think of it like allowing data to flow through based on all demographics. Because they represent the larger data set, not just a sample data set. But this is one to express here formally. It's basically a way to giving us a function work on each part of the function. For example, like you got something that depends on dependent. If you have something you're studying, a case study, you're working in a real world, and you're working on to determine why neurodivergent people in the UK are suffer from autism, and in other Nigeria they don't. Or in America, why things are very from demographic to demographic, you know the neurodivergent people in the UK, you could argue that neurodivergent people in the UK suffer with autism because there's a lack of support structure by the local authorities. And but Nigeria doesn't have those local authorities, so that input is a bias. because that implies a bias. Because the bias of the neurodivergent people having support in the United Kingdom does not justify why all the local government authorities and how they function. Because we have a centralized government in Nigeria, and that is in the cities. But in less rural areas, the councils still have a duty, but the councils don't do their job. So how would you expect this input to be? This input is a null state. It's a null input because it doesn't exist for all the cases, all the real world cases. And that's where the bias promises come in. They come in to ensure that the test is equitable. So instead of asking that question, you can ask a different question like, why do why do neurodivergent people? One way to do it, you can ask a different question, or you can structure the question, but with the bias parameter. The bias parameter based on demographic. Why don't neurodivergent people in the Nigeria suffer from autism? From the UK, those questions are really how you phrase the question is really important because it guides your research, what you do next, what your action will be. So this is a system that knows what is wrong, and this is a system that knows that transparent network, Bayesian outcome, hidden bias in the system, or pay processing, but controlled factors. These are the confounders. These are the things you can control the confounders because that's how they perform the test, and the confounders are controlled by the referential of I won't say priors. The control factor is the confounders. How the confounders were things that were formalized in the aspect of the case study, like how the formulation, how the confounders fit into the case study, because the confounders by definition are systems are a way to know. The confounders confounders provide a way to test something at the gray area, like something that doesn't really match up, because it's influence is basically there, but you're not measuring it. You are your question does not uh um uh, uh, address it systematically, So this is the unbiased model. This is AI biased as pattern learning, because you have a pattern recognition, you feed it to a machine learning model, and the machine learning application, and you have a bias output. We have an amplified bias at the end of it, and you have a feedback loop into the training system. This is basically when you're doing on supervised learning. Or supervised learning. Supervised learning means you're watching data set, and unsupervised learning means you're doing reinforcement learning. You have a feedback loop. But you have to tell the system via how to train a data device. You can recognize an image of a cat or a dog. This is the formula here. Fx converted to argmax y, root of y x given 0 or 0, given x colon 0 colon theta. What does theta implies? Yeah, theta is the bias. No, MLR. Basically, this is all pseudocode that uh um that handle the kind of model that predict uh you know but this is this thing was time for I don't remember. uh but this is for each sample x and y of an element of D. Do compute prediction y equals f s comma theta. Calculate loss L of function x given y. This is the monotone function of increase of y. So this is like a function y being computed to the scale of y, and update theta to minimize L, which is the loss. And for one of which bias pattern. So this is the result. This is the result. But this is all pseudocode for now. This is all pseudocode. But this is the of film I'm giving you. So we're gonna have the pattern learning is application of bias. So you don't use pattern learning. You have to use because recognizing patterns doesn't really mean you really understand information. That's what I'm trying to give you. Recognizing patterns doesn't really mean you are understanding information that they're giving you. You are just a text processor, the same as text that can reading patterns, just a better pattern reader, matcher. And that's what I'm giving you here. So the idea of this system is to show now you're gonna have unboxing through sensory data structure awareness. So you're gonna have pattern learning, and pattern learning will be, a bad practice. This is a bad practice. So it's pattern learning is not very good for AI systems. But you can every time you see this kind of code, and this is a bad way to, it's good for AI. AI systems can use pattern learning, but AI models cannot. AI itself, which is not machine learning, should not use pattern matching. So you have a 4D tensor, pattern learning and pattern matching. So this is my implementation. This is 4D tensor. This is very important to understand. A 4D tensor can have four dimensions of input, x, y, z, and w width. All dimensions, or you can have x, y, z, I for index, or you can have it's a vector 4. But the serialization over vector 4 to 3 is a Canaan cluster via a nearest neighbor clustering dimensional relations. Again, a 4D tensor can be reduced to a 3D map, a 3D tensor, a 3D map or tensor, because it's just that depending on the classification of the problem, you have a high dimensional representation for the same 3D information, 3D tensor map representation. And this paper explores how this solves the problem. So you're gonna have a KNN cluster which is near K, and you gotta have N nearest neighbor, IJ for nearest neighbor. Well, this is IJK. We have N. If you have K, IJK, you have K nearest neighbor clustering, which is a knowledge graph, which is semantic graph, edge-based clustering, for a system, because it's basically a KNN clustering algorithm based on graph theory. And graph theory represents these as tripartite clusters. So you usually have something that's can be considered miscellaneous. So these are things can do with outliers in a data set. These are kind of because they work on clustering information into categories, and you can have a category that's miscellaneous, and the AI system can tell you, oh, this is miscellaneous. I don't really understand what information is here. And this hypothesis one, AI, no, hypothesis one, hypothesis two, hypothesis two, unboxing through structural, data structure awareness. It's not even a unboxing. It's basically an AI model. Basically the system knows it's aware. It's aware of what it's processing, based on ontology, knowledge graphs. But knowledge graph have semantic context, hold semantic context. So they have a still that I can't remember the definition of a knowledge graph, but I can find it from the 4J book. The new 4J book I wrote. And you have the 3D classification of the same 4D tensor set, because at a point, at an interval, a point in time on space, so you can always measure. Basically, this 3D map also represents mapping it to a 3D system. Basically, because you have a 4D tensor and you have a 4D tensor, the world is 4D. 4D. You can have a 5D. If you are working in a 5th dimension, you use a 4D tensor. If you're using a 5th dimension, if you're working in a 5th dimension, you consider. Think about a video game. If you have a car, no, a real world car, not a video game, driving down the street, and then that car is you processing the 4D tensors. That information is good enough to process a 3D tensor. have to reduce to a two-digit number. The rule X, Y, Z condition is to be operate at a point in time, interval in time. You can separate the 3D tensor from the 1D tensor, but the next one should be the 3D tensor multiplied by 2D tensor, which is basically a matrix. A 3D tensor multiplied by 2D tensor. So, 2D tensor 3 by 2 matrix or 3 by 1 matrix, 3 by 3 matrix, never 3 by 4 matrix, because dimension reduction replaces reduction of dimension in by classifying tensors as semantic understanding in real time. So no extra information is spent. No extra resources. It's really computationally friendly for the computer to use matrices to perform these kind of operations I'm talking about. So this is a high dimensional data processed in instructional box and semantic layer. So what's very important is basically the knowledge graph of the RDF resource differential framework of the graph that's used in semantic understanding. But this is basically the system. So input 4D tensor, semantic structure map, apply k-lens clustering, group by data by similarity metrics, transform the tree representation, ungroup for semantic content. Basically, you have structural unboxing for structured data. I have unstructured unboxing for unstructured data. But the data, basically, the data is basically unboxing refers to the term of getting information out that is meaningful. So you get an unbox, or box if you're even, but you don't keep unboxing unstructured information. So if you think about unboxing as classifying information that is structured. But the structure means the information is structured. So you're just pulling information from inside for meaning. So you have interpretation of information via knowledge graph. And you have the semantic graph structure. So you have that. So hypothesis 3. AI systems suffer from this. And this is basically base ALLM, visual model, visual voice interface, attribute features, robust visual. This is basically something that you can use to control robots in real time. Model requirements, you call LLM. For each require you do, identify identify models from true directory, load models dynamically, connect to voice call system, validate integrity. This is a polyglot system for AI models, and it's ability everything to be loaded, dynamically loaded, once they are interfaced or plugged in by the driver, or a diffusion module, the voice interface, the attribute feature, so you can detect real world classification of data, which is the model, the voice interface, and you have that. So you have this one here. Probability of T given S, C, and A equals to root of T given CT dot the the probability of the prime probability of given A. This is this is a bias path. So the probability of theta, the data, traditional argmass up based optimum, bias optimum. Probability Bayesian, this is the probability, this is basically the Bayesian one. Basically, traditional approach of this is the traditional Bayesian version. Is basically the system of bias detection AI. So you can detect bias in AI by optimizing the probability. So this is probability of data given the data set D is equal to the integration of probability of data given psi of the data given the taking the derivative of d of d psi. Yes. So this is the integration of system. This is Bayesian probability distribution of the system. This is not really a clear cut. This is not really clear cut. This is very very this is basically not really comparison traditional versus bias. But this graph is very biased. So I can't use the graph now because I'm streaming right now. I'm just like but the graph, what it means is that the posterior distribution and the posterior distribution, this is prior logic, Bayesian priors. What is a prior? What is a prior in Bayesian? Bayesian. Prior. This is this. prior and posterior as probability itself. Information prior. The prior pre-existing knowledge of the data problem, the study likely to consider non-informative priors designed to minimum first on the priors. Speaks for itself. Example: uniform include uniform distribution for flat priors. Basically, posterior mean choosing a prior. So this is the kind of mathematics I do to express the thing from them. I'm just trying to research this. But the priors are literally definition are they are informative, non-informative priors, and they are pre-existing knowledge. Information priors are informative knowledge about the parameter. Example: if the prior such as parameter is likely to be a certain grade, this information will be encoded into the prior distribution. And the non-informative prior, the system influences speaks for itself. It's a prior distribution. It's a traditional optimum. It's a Bayesian integration. And you have the price here. So you have optimized traditional price. We have demographic fairness, but this is the formal proof for the system. So this is the for the marginal procedure. Obviously, if you have a baseline, for theta given d, the intuition of p theta given the data set d phi as one system given data set d derivative equals derivative of d0 d theta given psi times this is Bayesian. This is the Bayesian probability. This is Bayes theorem given data, and this is the margin posterior is equal to 1 over p data set, where p data set is the growth from between 0 and 1, but it's basically the marginal portion between 0 and 1, and but this is represented as an integration form of the system as computational steps of systems, which is basically integration of p given the data sets theta given psi given the full given the full data set of data is psi p given the data set of psi data set p given theta given psi p given data or the derivative of theta. Now this is basically the combination of the system here. So this is the base. This is the Bayes theorem, which I mentioned here, and this is the probability distribution of it. So that's the conclusion for it. But you're gonna have other ones too. So this is my work. You can get the repository here, Uche. Uche. I'm looking for Uche. Basically, this is my work on ontological Bayesian intelligence. This is all my work here. So you're gonna have you're gonna have all these proofs here. That represents the filter flash monotone and hybrid mode convergence. You're gonna have the monotone, the bounded. So you're gonna have the cost function properties, the runtime cost, error cost stability, environment stationality. This is the finish. This is basically the proof of the AI system. This is 3.1. You got 3.1, you got 4.1. I need someone to see 3.1. 3.1. Filter flash monotone on the assumption of 1 to 3 for fixed environment distribution and monotone construction, increasing epistemic confidence. Proof of confidence monotonicity increases the average of the filter of a flash. Formally, the change in probability E P given E epsilon no E. What's E defined as? E given C flash minus E or epsilon. I don't think it's called epsilon. It's E given the cognitive filter. C flash. As non-distribution in P proof proof established one of the three Bayes ratio cohesion and property of monotone loss function. So define the cost advantage. Analyze a cost differential. Basically, for the error cost, these are all my arguments in the formal mathematical framework. But this is 3-1, 3-2, and 3-3. This is the proof I'm talking about. This is the work I really want you to verify. Uh, uh, but this all proves it out. You can explore this proof out here and using 3-5 cycle. So without further ado, let's continue. So, this is today's date is the 20th of May, 2026. The time now is 7:07. So, the ontological Bayesian intelligence is a system that knows itself and knows what it's doing, whilst operating. It's something that I'm trying to work on to determine how robotics interfaces and AI systems can be blended into one technology seamlessly. But this is just the AI interface. This is just the AI interface. I'm trying to build this AI myself, but I've got the proof already. I've already done research. So basically, if someone in my constitution has a disability, they are assisted by AI because AI systems are the go-to assistants. They're meant to enhance you, and by enhancing you, you read out words, yeah, it enhances your reading ability. You write out words, yeah, enhances your writing ability. You speak incoherently, yeah, it enhances you so you can speak clearly. That's the whole vision I'm envisioning. Because ontological Bayesian system, it knows itself and it knows you. It knows me. And that is the UAI. The AI is you. It's you. It's a reflection of your state, your ambitions, your goals, your dreams, and your values in the real world. Thank you for watching this video.